So welcome to my channel on technology space with machine learning and artificial intelligence. So the today's topic is apparent center of gravity in ships. So this is the second part of a two-part series. So this is also part of this maritime technology playlist. So let's recap a summary of the information that we have discussed in the part one of this series. So the link to the part one video will also be placed on the description of this video. So you can, if you're interested, you can go back and read that video first. So in that video, we considered two situations of a rigid body. The first situation is the rigid body with reduced mass. So the second situation is the rigid body with added mass. In the reduced mass situation, we have described that when rigid body is under partially submerged in a fluid, it may feels like it may have reduced some weight in that rigid body due to this buoyant force. So because of that same reason, the center of gravity in that rigid body will move away from that reduced mass area. And the second case also we briefly introduced. What we have mentioned was if we are adding mass into this rigid body, which is added mass into this rigid body, so the body itself feel like it has its own weight has increased. Due to that reason, its center of gravity would shift towards the added mass. So as you have noted, due to this mass configuration changes in the rigid body, the center of gravity position will change. So because of that reason, I think we were introducing this new concept of apparent center of gravity in that video. So we're going to discuss this added mass situation more detailed in this second video of this series. So let's try to recapture a little bit more information from the previous video. So that reduced mass situation was created due to this partially submerged rigid body in this fluid. So in that situation, we also mentioned that the buoyant force, which is acting against the total weight of the rigid body, is equal to the density of the fluid times the submerged volume times the gravitational constant. So in the situation where the rigid body was partially submerged in this fluid, we assume that the fluid and the rigid body are in a static condition. So if you think about a situation where we are applying external force, which is F1 in this figure into the scale and try to pull this rigid body out of this fluid, what could happen? So these are the effects we're going to discuss one after another throughout this presentation. So the first thing you could notice, since there's an external force applying in this rigid body, so the rigid body start to accelerate. So the acceleration is represented in this figure by A1. So the external force is represented as F1 in this situation. So let's see what could happen to the buoyant force due to this external force. So when the external force is pulling this rigid body out of the fluid, so its partially submerged volume would be reduced. So due to that same reason, the buoyant force will also be reduced. So the new buoyant force in this figure I am represented by UNF, which is equal to the density of the fluid times the submerged volume. In this case, the submerged volume, new submerged volume would be this VF minus dVF. So the dVF represents the rigid body submerged volume reduction in this situation times the gravitational constant. So due to that buoyant force reduction, the rigid body could feel like it has gained some weight. So the new weight of the rigid body would be represented by WNF, which is equal to the W, which is the original weight of the rigid body, minus the new buoyant force, which is the UNF in this situation. So since the rigid body is getting a new weight, that number should also be reflected in the scale reading. So the scale reading also will represent the same number in this situation. So when you're applying external force and trying to pull out that rigid body out of this fluid, we have discussed in the previous case, the first effect could be that buoyant force can be reduced. Because of that reason, the rigid body can feel like the weight of that rigid body has increased. So the second effect would be this added mass. So when the rigid body is trying to move out of the fluid, what could happen? The fluid volume around that rigid body try to move along with that body itself. So that attachment of the fluid volume to this rigid body would act as the added mass in this situation. So the more technical definition for the added mass would be the added mass is the inertia or the mass added to the rigid body because of its acceleration or deceleration conditions in the surrounding fluid. So as I have mentioned, the volume of the fluid is trying to move along with the rigid body in this case, and the added mass always will work against the acceleration. So in basically the rigid body could feel like additional mass has been included into itself. Due to that same reason, the weight of that rigid body will increase. So in this situation, I am representing added mass as MA. So therefore, the added weight would be WA, which is equal to the MA times the gravitational constant. So the new weight of this rigid body is also represented in this situation. So the new weight of that rigid body would be WNF, which was the initial weight of that rigid body, times the WA, which is the added mass in this situation. So you should note that this weight variation should also be reflected on the scale reading. And then when we included added mass into this accelerating body, so it feels like the weight has, or the mass distribution has changed. So because of that reason, the center of gravity of that rigid body moved towards that added mass, as we have discussed in the previous video. So you can see again in this situation also, the location of the actual center of gravity has changed due to this added mass or the interaction of that rigid body with this fluid itself. So the third effect when we are trying to pull out that rigid body from out of this fluid would be the drag force. Drag force can be seen as a situation you will get this frictional type of a force along the surface of the rigid body due to this surface and the fluid interaction. So this can be seen as some type of a frictional force, and it could apply throughout the surface, underwater surface of that rigid body. So there are three effects that could influence this rigid body due to a situation where this external force F1 is trying to pull out that rigid body out of this fluid has been discussed. So the first effect was that the buoyant force UNF is working against the weight of the rigid body. And then the second effect was the added mass, which is WA, working against the acceleration of that rigid body. And the third force is the drag force, which is also working against the acceleration of that rigid body. So these force variation should be reflected on the scale reading. So as you may have noted in the scale, the summation of the forces should be reflected. So that is noted as the W, which is the original weight of the rigid body, minus UNF, which is the buoyant force of that rigid body. And then added by WA, which is the added mass, also added by FD, which is the drag force in this situation. So that is what the summation of these forces is going to be, which is reflected on that scale. So there's another important point you should also note it. The F1 should be larger than this force summation. So that is the only way this rigid body could have the acceleration A1, which is into the same direction of the external force F1. So let's try to understand another situation where this external force F2 is pushing this rigid body towards the fluid. So what sort of effects this fluid body can encounter? So the first thing you could note is due to this F2 force, the rigid body would get an acceleration A2, which is also acting downwards as the external force. So the second effect could be this buoyant force, which is UNF. Due to this F2 external force pushing that rigid body downwards, the underwater volume of that rigid body, or the submerged volume of that rigid body, could increase. Due to that reason, the buoyant force value will also increase in this situation. So the next effect could be the added mass. Since this external force is pushing that rigid body towards the fluid, this added mass could work against the acceleration of that rigid body in a different shape than the previous case. So the next effect could be the drag force. Like in this previous case, this drag force will work against the acceleration of that rigid body. So like we discussed in the previous case, due to this mass distribution variation, due to the buoyant force and the added mass, the location of the center of gravity in this situation could also change. So the scale reading should show the summation of the forces acting upon this rigid body. So these forces can be summarized as that weight W, which is acting downwards, minus UNF, which is the buoyant force acting upwards, and then the added mass, which is minus WA acting upwards, minus FD, which is the drag force acting upwards. So you should also note that the summation of these forces should be less than the F2, which is the external force. So that is the only reason for that is when this rigid body is having the acceleration and the external forces are in the same directions. So that condition should satisfy. Anyway, in this scale, this is a compression situation. In real life, it may not be reflected on the scale itself unless it has some sort of a negative value and showing that this is a compression situation. So let's try to complicate the previous situation further. In here, we are applying this external force Fx back and forth into this rigid body. So based on that force direction and the size of the force, the rigid body will also get acceleration Ax in this situation. So when rigid body is moving with some accelerations in the fluid itself, there will be three effects will come into this fluid body itself, as we have discussed. So the buoyant force UNFX will always work against the weight of the rigid body, so it's having the same upward direction. But the drag force Fdx and the added mass Wax will always work against the acceleration direction. So in this situation, the weight of the rigid body could change. So since the weight is changing, the mass distribution in the rigid body will change. So due to the same reason, the center of gravity in this rigid body will change. So this is a good place to introduce this apparent center of gravity, showing that the actual center of gravity of the rigid body is varying due to this rigid body and the fluid interaction in this situation. So up to this point, we have discussed this rigid body translational motion under external forces, but there's a possibility that internal and external forces can work out some sort of a movement, and then the rigid body might go under rotational motions. But we have not discussed that concept in the previous slides because to keep those slides somewhat simpler. So here we are trying to discuss that when we are applying a movement, in this case this M2 into the rigid body, what that could affect on the rigid body itself. So one more important point about this figure would be when we apply that movement M2, the rigid body itself start to rotate around a specific point. So since it is start to rotate around that point due to this movement M2, that means rigid body is getting an acceleration due to that external movement. So this acceleration can be divided into two sectors of translational acceleration as well as the rotational acceleration. In the translational acceleration, we are dividing these accelerations into two components, which is normal and tangential accelerations. These two translational acceleration components are noted by A4 and A3 in this figure. So then move into the rotational acceleration, which is defined by A5. So both translational and rotational accelerations are acting upon that center of gravity, but I mean the whole, if you select the different points around this rigid body, these points can have a different acceleration and acceleration conditions, including the rotational and translational accelerations. But in this case, the rotational acceleration is denoted by A5, and it is applying around that center of gravity in this situation. So let's try to understand what other effects could happen on this rigid body due to this movement M2. Since this object, the rigid body start to rotate around a specific point, what could happen, the sector of the rigid body may be submerged and another sector may be raised from the water surface. Due to that, the buoyant force can vary, and then that eventually affect on the total weight of the rigid body itself. And then if you're looking into the added mass will work against the acceleration of this rigid body. And these situations, we are assuming that no translational motion of the rigid body. Otherwise, this added mass application could be somewhat more complex. And similarly, the drag force will affect on this rigid body against its acceleration conditions. Here we are more focusing on the rotational acceleration conditions of the rigid body, but there can be effects coming out of the translational acceleration conditions also. So as we have discussed in this previous situation, due to this movement on the rigid body, it could get translational and rotational accelerations. And then these accelerations eventually influence on the added mass of this rigid body. Similarly, that will also influence on the buoyant force. So since this buoyant force and the added mass will vary in this rigid body due to its rotational motions, the weight distribution or the weight condition of this rigid body could also vary. Since the weight is changing in this rigid body, the mass distribution will also vary accordingly. So therefore, the outcome would be the center of gravity. Position could change due to this mass distribution change, due to this rotational motion of that rigid body itself. So let's try to combine these varying external forces and movements into a single rigid body. As you may have noted, this rigid body will encounter somewhat complex motions due to these external forces and movement. So the first thing you may noted in this rigid body could be it may have a translational and rotational acceleration at its center of gravity due to these external forces and movements or acting on this rigid body itself. So the other forces like the buoyant force, the added mass, as well as this drag force could vary accordingly to these acceleration conditions. So the buoyant force, as we have discussed previously, in some situations, some part of the rigid bodies can submerge, another part may be raised from the water surface. So due to this effect, the buoyant force change accordingly. And then if you are looking into the added mass also, due to these translational and rotational accelerations, the added mass could also vary accordingly. So similarly, the drag force acting on this rigid body will also change due to this translational and rotational accelerations on the rigid body. One important point, these added mass and then drag force will always work against the acceleration direction of that rigid body. So finally, then since the added mass and the buoyant force will vary due to these external forces and movements, the total weight of this rigid body will change itself, then its mass distribution will change. Due to these changes on the mass distribution, the center of gravity will also change in this rigid body. So then this rigid body is moving under translational and rotational motions under these external forces and moments. Some interactions on the fluid surface and then the rigid body itself being ignored. Now we are going to introduce such type of conditions into this figure. When the rigid body is interacting with this fluid itself, under translational and rotational motions, there's a higher possibility it will create waves under this fluid surface. So these wavy conditions can further complicate these rigid body motions, both in the translational and rotational directions. So you can imagine when these complications are influencing the rigid body motion itself, that will also influence on the buoyant force as well as the added mass and the drag force in this situation. So one should also note that these wave conditions can be incoming wave conditions in some situations. So what could eventually happen, these wave conditions in this fluid surface can further complicate the buoyant force of this rigid body as well as the added mass in this rigid body. Don't forget this drag force will also get influenced by these wave conditions. Since the buoyant force as well as the added mass could vary due to these wave conditions, the total weight of the rigid body can also vary. So varying total weight can influence on the mass distribution of the rigid body. So due to that mass distribution change, the center of gravity in this rigid body can also vary in this situation. So now you noted that due to these external forces and movements in this rigid body, how complex the location of this rigid center of gravity can be. So therefore, I think this is a good situation. We can introduce that concept of apparent center of gravity, because it is not exactly the center of gravity of the rigid body itself, but due to this rigid body and the fluid interactions, the apparent location of the center of gravity could be somewhere else. So that's why I'm introducing this concept into this discussion, as well as elaborating how and why it could happen. So that way, that concept we can utilize in the further for shipping industrial applications. So let's assume that the rigid body that we have discussed so far is an ocean-going vessel or a ship. So the water tank that we have considered in this example is the navigating waters of that vessel. So when these vessels are navigating in this ocean environment, its rudder and propulsion system can create forces and movements. Beyond that, when these vessels are encountering wave and wind conditions, these external factors can influence these vessels by having various forces and movements. So in our previous video on maritime terminology, I have discussed that these vessels can have 6 degrees of freedom. So that means 3 translational motion and 3 rotational motions. So in these 3 translational motions of surge, sway and heave, these vessels can have external forces. The 3 rotational motions of roll, pitch and yaw, these vessels can have external movements. So not just the incoming wind and wave conditions, but also when these vessels are navigating in calm weather conditions, these vessels can create wave itself, and then these vessels can also interact with the ocean waters. So due to these interactions, as we have mentioned, there were 3 translational motions and 3 rotational motions can be created. So under these translational and rotational motions, there would be 3 translational accelerations and 3 rotational accelerations can also be created. So these accelerations can make these vessel motions somewhat complicated as a 6 degree of freedom system. So as we have mentioned in the previous slide, there are 3 translational accelerations and 3 rotational accelerations will be influenced on these ocean-going vessels. as a 6 degree of freedom systems. So what eventually could happen due to these interactions, the added mass and the buoyant force acting on these vessels could vary. So therefore the weight condition of this vessel can also vary. In addition to that, the load condition of these vessels can also vary due to the cargo it's carrying or additional requirements in these vessel operations. So all this combination could eventually what happened, the weight of this or the weight distribution of these vessels will vary. So due to that weight variation, the mass distribution in these vessels can also vary. So when you have a change mass distribution, eventually the center of gravity location of these vessels can vary, not just due to the environmental conditions, but also due to the load conditions of these vessels. So therefore, because of this reason, we have introduced this apparent center of gravity concept into these vessels. In this figure, I am denoting that apparent center of gravity as a CGA. And then this concept we will utilize throughout our future slides to highlight that vessel itself can have a center of gravity, but when it's navigating in a more complex environmental and load conditions, the center of gravity can vary, and then variation is introduced as that apparent center of gravity in this situation. So that's the end of this long presentation. I think this topic is really important because when we are talking about ship motion and control applications, the apparent center of gravity concept is really important, because when it's changing throughout the vessel body, it would be difficult to apply some of these kinematic and dynamic equations in these vessel motions. I mean, we have to find solutions to this research challenge. So that was the reason I was highlighting this issue in these two presentations. So if you're still interested on these topics, please stick around. Thank you.